Okay. Okay, there are 40 people. I feel like that's a good critical mass to start. Okay, so yeah, thanks for your messages. I hope you're going well. Please get some, um, maybe open the window if you're in Dallas because it's really nice. This is like very rare for it to be this nice. Um, I hope the office hours have been going well. I've talked to Trisha and Anya, uh, and they have said really good things about the office hours and that people are enjoying and people are asking good questions. So keep it up. Someone is asking, is there? Yeah, there are some people. There are some people from Florida. From I guess one person from Florida, a few people from Baton Rouge in Louisiana, some people from San Antonio. So yeah, we have a good mix. But most of us are from Dallas. I'm in Dallas. Okay. So without further ado, can anyone remind us what we were talking about yesterday?
Absolute value.
Yay. Okay. Yeah. Very good. I have my computer connected to a speaker, so you might be able to hear yourself. It's kind of loud here. What are the English tutors? Okay, so I guess we're going to deal with some organizationals. What are the English tutors? I really don't know. Did you guys have the English lecture today?
Yeah.
You did. Okay. How was it?
Good.
Okay, great. So ask Pratik. Yes, email Pratik. I have no idea what's going on with the English class. I wish I did. I'm technically in charge of the entire thing, but it's we split. Pratik and I split the camp into half. So he's doing English. He's in charge of all that. Okay. Okay. So yesterday we talked about absolute value. And okay, let's just review very quickly. Okay. So okay, I'm having a hard time with like going on with the lecture and answering questions. So yes, Leanne, Anya is a math tutor. So go to the website, which I feel like I post a link every day. I hope everyone has the website link. It's on like all my emails as well. Okay, if someone doesn't mind just posting that in this chat, that'd be great. Yeah, so Anya is a math tutor. They're all assigned. I feel like I say this every day, but people might not be hearing me or might not be present to hear. But yeah, it's assigned alphabetically by first name. Thanks, Adi. Thanks a lot. Yeah, so if you go to that webpage and you go to contacts, you'll see all the tutors and their wonderful faces. So you all should know that like all these tutors, these are all like friends of mine. Okay, so we're all actually friends. I was talking to them this morning actually. We're friends before we're like like math people or whatever. Okay, so we're all having a good time. We were talking about you all. We're like, oh yeah, this guy's doing really well, and maybe we can do a better job explaining this. So yeah, we're all okay. Anyway, so yeah, so absolutely. So what are the three definitions? Number one, it doesn't have to be in any order, but we had three definitions of absolute value.
Square root of something, negative something squared.
Does it have to be negative something?
Oh, yeah, positive something.
It doesn't have to be positive something.
Oh, it can be anything. It's plus minus.
Well, yeah, it can be any. Okay, we don't talk trash about you, no. But we do like, okay, sorry, Adi. This is, I feel like I really want to get to know you all. And yeah, anyway. No, we don't, we love you all. Okay. So the absolute value of any number, call, okay, let's use A for Adi. Are you talking? Is that you?
Yeah.
Okay, so A squared. And this is that. And this is the same thing as this. You realize, right? Because the square and the square root are inverse operations. Yeah. Selena says distance from 0 and variable x if system, but I forgot that. Okay, good. So you gave us the remaining two definitions. So another definition of absolute value is like the elementary or middle school kind of, I guess more middle school, but yeah, it's a simplistic definition. And it just says that the absolute value of a number is sort of its distance from 0. This can also mean, on a plane, on a line, it's pretty straightforward to understand, and a middle schooler can really get that. But if you're in a plane and I have this point, what is the absolute value of this point? It's the distance from not 0, but this thing, which is, what is this called?
The origin.
The origin. Yeah, so it's the distance from the origin. And this is actually, this definition, if you generalize this sort of trivial definition to to a plane or to the 3D space or n-dimensional space, you actually get a non-trivial definition. And so Adi said x2 greater than or equal to 0, negative x. Okay, Adi, I'm not sure what you mean. But okay, it's okay. Okay, so what is this distance in the x and y plane? This is non-trivial, actually. So this childish definition of, oh, it's just the distance from 0, that's trivial. This is non-trivial. What is this distance? If this is the origin, and say that this is A column B or something. There's a famous theorem. It's like the most famous theorem in geometry that gives this distance. What is it?
Distance formula?
Which theorem?
Pythagorean theorem? Or distance formula?
Okay, so the distance formula is getting at it. And what else did you say?
Mind, Pythagorean theorem is for the triangles.
Well, this is a triangle, right? Because look, it's not just any triangle. It's a right. You can make a right triangle. Because we're in Cartesian coordinates, you can drop down. This is actually a projection, okay? I think, Adi, you mentioned the word projection yesterday when we were talking about dimensionality. You can project this line. It's actually a vector, but we won't get into that. You can project this down onto the x-axis and you get this thing, and you can project it onto the y-axis and you get this thing. And one reason we use the Cartesian coordinates is because these coordinates are perpendicular to each other. It makes for a very good coordinate system when your coordinates are perpendicular. And this is, so you might remember when I said orthogonal, okay, like a long time ago, like last week when we were talking about slopes. This is really the meaning of orthogonal. It has to do with coordinate systems, and it's really a linear algebra term. But anyway, that's getting ahead of sort of what we need. What is this distance? So what is this? So if this is the point A, B, then what is this? This is easy.
A,
How about this?
B,
Okay, so then what is the distance? What does the Pythagorean theorem say?
A squared plus B squared equals C squared.
So then what's the distance? If this is C squared, then what is? Sorry, this is not C squared. If this is C, then what is C in terms of A and B? Just take the square root, right? C is...
Yeah, A plus B.
No, it's not A plus B, it's A squared.
Square root.
Yeah, make sense? Okay, so this is a non-trivial thing. And there's actually a beautiful proof that I actually didn't know about, that Patricia, I'm going to tell her I told this to you all, because this is actually really cool. Patricia told this to, I don't know why I'm writing her name on the thing, but Patricia told me that there was a mathematician named Fermat, and Fermat was a genius, and he had a book. There was a book at the time, he was like 19th century, kind of 18th, 19th century, and he had a book of all the unsolved problems of math. It was like a huge book, and there was a list of like these hundreds of problems that were unsolved, and he went through the list, and he solved many of them. He was a genius. He just went through this list of things that people thought about for hundreds of years, and he just came out with solutions. And he wrote them in the margins. And so there's actually one of the problems was that if you have, like, say, three-dimensional space, and I have some, this is hard to depict because in 3D, I'm drawing in a 2D plane, but you can kind of visualize that this point out here, see, it's in three, it's like, there's like X, Y, Z. So it has three components, that this distance is actually x squared plus y squared plus z squared. It's a generalization, this distance, d. The distance is d, but d squared is this. So it's a generalization of the Pythagorean theorem, which is explicitly, when Pythagoras showed it, Pythagoras said it was in 2D. Fermat proved that this was true, and in general, that for n dimensions, you would have n of these terms, right? So a squared plus b squared plus c squared plus d squared, as many dimensions as you have. And Fermat proved this supposedly, but in the margins of the book were too narrow. And so he wrote, the margins are too narrow. And this has become like almost like an excuse It's really funny. I mean, when if you don't know the answer to a math question, you can just write the margins are too narrow, and people kind of laugh because they're like, oh, you must know how to do it, but there's not enough room. But Fermat supposedly actually knew the proof. Anyway, that's just an aside about this trivial definition. Okay, what's the third definition? I think Selena said this a while ago. The two cases. What are the two cases?
X is greater than or equal to 0, and negative x is less than 0.
Okay, we're using A for Audi.
Oh, okay.
So A is greater. So sorry. So you said the cases. You said the different cases, but the absolute value is equal to A if A is greater than and it's minus A if A is less than 0. And if this is still confusing you, pick your favorite number. Like what? Okay, like -3. Okay, so what's the absolute value of -3? From definition 2, the trivial middle school definition, we know that this is 3. But let's see if it fits this definition too. Look, -3 is A. So look, the absolute value of A is what this says, is -3 if -3 is greater than 0. Well, is -3 greater than 0? No, so this can't be right. And then if you put a -3 here, what's negative of -3? That's just 3. If -3 is less than 0. And indeed, -3 is less than 0. So this is the case that applies. And therefore, the absolute value of A is 3, of -3 is 3. So this is I'm just showing you that this actually works. This is a very nice definition. This is the complete, rigorous mathematical definition. Okay? Any questions so far? This is a review of what we did yesterday. No questions. Okay. Now here's a question, okay, that
So if this doesn't work out, then what do you do?
well, it's a mathematically, it'll always work out. One of these conditions won't be met.
One of them. So as long as it meets one.
Well, then it'll always only meet one.
Okay.
Even the case of 0, that's why I had this equal to sign, because we have to include 0. 0 can't be left out. So if you put in a number, you have to realize that, only one of these, you can't think about it. You can't have a number, I scribbled over this, but you can't have a number that's both greater than or equal to 0 and less than 0. You can't, like you won't find it. You can search the entire universe for this number, like big numbers, small numbers, whatever, negative. You won't find a number that satisfies both. That's the point. That's exactly the point. The absolute value can either be, just the thing that's inside the absolute value itself, if that thing is greater than 0, which makes sense, right? Because like if you picked 3 for A, then the absolute value is just 3 because 3 is greater than 0. But it would be, the other condition would say, it's -3 if 3 is less than 0. But that is false, and so this is not what the absolute value is. Make sense? So it takes some time to get comfortable with this definition, but the power of it is beautiful. Okay, you can do all these. Okay, can everyone hear me?
Yeah, there we go.
Okay, so for some reason it cut out. It did. What happened on your end? Did you see anything?
You just cut out, like you made like a really loud, high-pitched noise and cut out.
Oh gosh. Okay, sorry. I don't know what.
Stop talking.
Yeah, if the internet.
That's what happened.
What's that?
You just stopped talking.
I just froze. Okay.
Yeah.
Okay. Anyway, did you hear what I said about this?
Yeah.
Okay. Good. So now here's a question for you. Is the absolute value distributive? In other words, this is actually a question that Gabe brought up to me. Is the absolute value of A plus B just the absolute value of A plus the absolute value of B? Anyone?
No, that can't be true.
Yeah, and if you want to show generally in math, so Aruhi said yes. Aruhi, we're going to, I love it when people say yes, because this is actually, in math, it's very hard to show. Yeah, you're right. It's okay though. No, the point is that we're going to show you. Yeah, so Alexis is starting, I'm reading the chat by the way. Alexis is starting to, do exactly what I'm about to do. Generally in math, it's a lot easier to show things are wrong than things are right. Think about nature. I mean, nature, nature has a very specific way of acting, and you can come up with an infinite number of ways that nature doesn't act. And this is one of those ways that nature doesn't act. So yeah, so -2 and 1 to take, was it Alexis? Yeah, Yeah, Alexis, yeah. So look, does this equal this? What is that? What is this? This is just that. What is this?
3.
1 plus 2. So, and this is 1. So this is a contradiction, that 1 equals 3. Therefore, this statement is false. You can just, all you need is one, think about it. You just need one example, it's called a counterexample, to show that an entire statement is false. It's very powerful. However, keep in mind that if you find a could we have picked an example for which this is true?
Like 2 positive numbers, I guess.
Yeah, you could have picked like 1 and 2, and then it's true. So what does that tell? That tells us that just because you pick one right example, it doesn't show that this entire thing is true. So you need an infinite number of correct examples to show that this is true, but you only need one wrong example to show it's false. It's kind of like unfair, you might think, to truth. It's not like a two-way street, but this is actually a beautiful thing in logic. It's just the way the way nature is, right? Nature has a very specific way of acting. And so if you come up with some theorem or some formula, it needs to match every bit of nature. And if you find one example where it doesn't, then you know that.
So both answers do not match or do match?
Well, so for positive numbers, this is true. But what's the point if you're taking the absolute value of positive numbers? So this is generally not true. Yeah. Absolute. So in conclusion, the answer to this question, is absolute value distributive, is no. And we just showed by counterexample why it's not. Does that answer your question? Whoever started talking there. Yes, I assume so. Okay, so let's just do a few examples from yesterday, and then we're going to move on to our next topic. Okay, how would I start this? First of all, big picture. What is the goal in algebra? To solve for x, right? So what's in the way? What are all the things in the way from outside to inside?
Absolute value of sine 3.
Yeah, the 3 is in the way and the 2 is in the way. So first, let's deal with the absolute value. And how do we do that?
Make 2 solutions.
Yeah, so we use that second definition of absolute value, right? So this is just by definition, right? And I'm just going to do it because I assume that people will now have had practice with this. Okay, I'm not going to even write the conditions because you don't really need them. Okay, so if 2x plus 3 is greater than 0, if 2x plus 3 is less than 0. Okay, now I'm going to apply the right-hand side, right? This is the actual part of the problem. Someone emailed me yesterday and said, is this all we need to do? And that's a good question. No, that's not. All you've done is applied the definition of absolute value. Now you actually have to solve the thing, right? So I'm going to take my 2 cases. Sorry, less than 5. And the other case is right? And now I can solve each of these independently. So 2x plus 3, how would I do this? This is less than 2. And for the bottom one, I'm going to multiply across by -1. And we learned 2 days ago now that I have to flip the sign when I do that. Okay, and now this is like piece of cake. You've done this for yours. X is less than 1. Here I add, subtract -3 on both sides. So 2x is greater than -8. And then the solution to this is x is greater than -4. So you have this and this. And now if I were to plot the solution, 1, -4, and 0 would be somewhere here, right? And so open circles or closed circles?
Open circles.
Because the answers are not inclusive, they're exclusive, and I fill in the space in between. If you're confused about whether to fill in this side or this side, what I would do is I would draw little arrows above. So for this case, for the -1, you have this solution. It's all these numbers. And for this case, you have this solution, and it's all these numbers. So the part that overlaps is just, this chunk here. Make sense? I'm going fast with the math because I assume everyone can solve a basic algebraic kind of equation. Okay? Someone asked. I don't know what's going on. Okay, that's good to know. You don't know what, Isaac, were you here yesterday? No, okay, that's, oh shoot. Okay, I'm gonna send you the lecture. Okay, in fact, I'll send everyone the link to the lecture from yesterday at the end of this lecture. So Isaac, just hang tight for today. I'm sad that you couldn't make it yesterday because now today's gonna be kind of hard. But hopefully you just sort of get a feel for some of this, and then you can sort of, so yesterday I went really slow with all of this, and some people were bored out of their minds. Some people were not. Yeah, so Leanne, yeah, I think I'll send you the link. You don't have to go hunting for it. I'll send it to you at the end, okay? Just remind me. Okay, so this was a 1D problem. Now let's talk about a 2D problem. Right, so here my answer was on a line. It was confined to the x-axis, 1D. Now look, I have x and y, two dimensions. So my answer is going to be in the plane. And how do I do this? This is not an inequality. This is an equality. And how would I?
Isn't it already in like the slope-intercept form?
It is, yeah, it is already in slope-intercept form. And slope-intercept form is mx plus b. And so here's your m, your x is x, and here's your b. So there are two ways to do this. There are many ways to do this, but there are two sort of basic ways to do this. There's a smart way that shows that you know what's going on, and then there's a way that the computer does it. The way that the computer does it is it makes a table. And so if you're confused about what this equation is or what the absolute values are due to this equation, I would make a table. Okay, just follow what a computer does. So I would put in a bunch of values like -2, -1, 0, 1, 2, for example, for x, and I would put this into x here, right? So for each of these x, then you find y. So for x is -2, 5 times -2.
7.
Go ahead. Yeah, 7, that's right. How about this one? Putting -1 for x. 5 times -1. Yeah, 5, so 5, that's -5 plus 3, which is -2. Absolute value is 2. 0 gives you 3, right? 0 times 5 is 0, plus 3. Absolute value of 3 is 3. 1 gives you 8, right? 2 gives you 13. So you could plot these points. So -2, 7, -1, 2, 0, 3, 1, 8, 2, 13. So what's the general shape?
A V.
So yeah, it's something like this. Something, I don't know. The thing is, with this method, you have to take a bunch of points to really figure out what's going on in this yucky region, right? Because I don't know if it turns here or if it turns here or if it hits the axis. I don't know. So you see why this approach can be kind of goofy? It's like you kind of are guessing. This is what a computer does, but see, a computer can take an infinite number, not an infinite number, but it can take 10,000 x's, say, and then it can make them all really close together, and then it can give you a nice plot. That's how a computer plots things. Okay, but what's the smart way? The smart way is to look at patterns and say, okay, well, we know that this is kind of like y equals mx plus b. So if I plotted just this, right, if I just plotted this is easy. We did this the first week of the course. The slope is 5 and the x-intercept is 3. So it looks like this. This value is minus b over m, which is -3/5. And now look, when you take the absolute value of this entire thing, well, the absolute value can't be negative. By definition, the absolute value is not negative. So the negative part just gets reflected across the x-axis. So all of this stuff just gets, it's like a mirror. The x-axis becomes like a mirror. You can think of it like that. See, like a nice mirror, you can kind of see. Yeah. So look, I got the same thing in minutes. I mean, this was simple, right? I didn't put in any points. I didn't really even think. Make sense? So the latter way, so I started with the normal linear equation, and then I stuck absolute value bars. And I said, oh, well, when you stick absolute value bars, all you're doing is taking all the negative y values. These are the negative y values. And I'm just reflecting them, right?
So what is this topic called, like the lesson?
Okay, so today we're covering two things that are not related to each other at all. And right now, all we've covered is absolute value.
Okay.
which is really yesterday's topic, but I went very slow yesterday because it was new to some people, to most people, I think, to probably all the 9th and 10th graders, at least the formal definition, right? So yeah, so we're gonna get on to new stuff, but let's try just a few more examples. How would I do this? Is this, first of all, the same thing as this? Look. Yes or no?
No.
Which no, it's not.
No, it's not. You can see that. Remember, we said that the absolute value is not distributive. Like absolute value of a plus b is not the same thing as absolute value of a plus absolute value of b. Well, someone who thinks that this is true, which is not, someone who thinks this is true would say that this is equivalent to this. And so we're gonna, if we plot this and show that it's a different graph than this, we'll have also found a counterexample for this statement, right? So anyway, so that's kind of the big picture. How would we solve this? How would we plot this kind of thing? Using a table, yeah, sure, but there's no math in that, right? That's just computer work. So how would I do this maybe? Well, I know what this looks like. We plotted this yesterday. What does this look like?
Just a V that
It's
originates
just
an origin.
It's just a V. And if you don't know why it's a V, then just plot this, which is just that, the parent function that goes through 1, 1, 2, 2, 3, 3, right? And then look, when you put the absolute value bars on, all this stuff just gets reflected. It's the mirror thing again, right? All the negative y values just become positive. That's what the absolute value does. So I've plotted right now, I've plotted y equals absolute value of x. Now, the different colors will be useful. So that's what that is. Now I'm going to think about, okay, what do these numbers do? Well, what does plus 3 do?
It'll increase the y.
Yeah, all this does, and you can verify for yourself by putting in points. But what this does is it just bumps the graph up by 3 units. So the entire graph, instead of being at 0, 0, 1, 1, so on and so forth, this point gets bumped up 3 units. So this becomes 0, 3. This point becomes 1, 4. So I'm just adding 3 to the y values, right? So now this graph.
Yes, I see your face.
Okay, whoever's like, I couldn't hear that. Okay, you have to talk clear. I could not hear what you just said. Okay, and then what does a 5 do?
It basically makes it thinner, but like it's stretch. It's a stretch.
Yeah, it makes the entire line steeper because this is sort of the slope now, right? So the entire line becomes steeper, and if you want to find what the points are, then you could just multiply. The 5 has the effect of stretching the graph vertically. Okay, the 3 has the effect of moving the graph up. Okay, so we're going to talk. This is the sort of what I'm talking about is the method of transformations. So you can think of sort of, if you look at this, you can think of the parent function, and then all these other extra numbers are just transformations on this parent function. It's a very efficient way to graph things. And I really shouldn't have asked you about the 3. Anyway, we'll get way more practice. We have an entire week on graphing, and we're going to get really good at this method. So this is just an introduction, okay, to this sort of method of transformations, okay? This is a problem from your homework, okay? And I'd like to just do it. It's actually not hard, but you can make it hard for yourself if you want, okay? But looking at this, can anyone immediately tell me what the solution is?
X is less than -3. Negative, yeah.
It's actually wrong. Okay, so how about I'm gonna give you a number that's not in this range. Like, how about -2? Put in -2 and tell me what you get. 2 times -2.
That's 4.
Yeah, and isn't that greater than negative?
Yeah, it's no solution, I think.
It's no solution. It's
Oh.
even worse. That's actually a worse. You just told me a worse answer than your first answer, because your first answer had some of the right answers, but no solution is actually none of the right answers.
All real numbers?
All real numbers is right, and why?
Because when you graph it on the number line, it just shows like all of the numbers.
Oh, so you actually graphed this?
Yeah. On the line.
Did you use like a computer, which is fine?
No, I like wrote it out.
You
No.
drew it out. Okay, nice. So that's one. You can draw it out, but you can also just look at this and ask yourself, is it possible for any absolute value, A, for absolute value of any number, A, to be less than 0? Is this ever possible?
No.
No.
No. And what is this number? Is it greater than or less than 0?
Less than 0.
Yeah. So is it possible for, look, even if I added the 1, subtracted the 1 on both sides, look, minus 1, what do I have? I would have 2x plus 1 is greater than negative 5. Negative 5 is certainly less than 0. Is it possible, I'll ask you again, is it possible for the absolute value to be less than 0? People are saying,
No.
okay, Nishan, I'm not sure what you're saying in the chat. Yeah. Anyway, yeah, no. So the answer is no. So immediately you know that because this absolute value, so in other words, if it's impossible for the absolute value to be less than 0, the converse is true, that the absolute value is always greater than or equal to 0, right? So Leanne, no, you don't have to show your work. No. So look, these two statements are the same thing, right? So first of all, this statement is never true. This is a false statement. So this is what remains. This is what's true. So in other words, the absolute value is always greater than 0, and this number is a negative number. So and the negative number is less than 0. So this thing better be greater than that negative number. And in fact, no matter what x you put in, because of the definition of absolute value, because a is always greater than or equal to 0, any a, or in this case, any x satisfies this equation. So that's sort of the logical way to think about it. Sorry if it was more convoluted than needed. Alexis says, if you have one false statement, it is an extraneous solution. Okay, I'm not sure what you guys are talking about.
There can't be extraneous solutions to this.
Yeah, so extraneous solution is something that we'll talk about in the quadratic, when we talk about quadratics and higher order polynomials. Extraneous solutions are not mathematical. Extraneous solutions come from like physics and engineering and all that junk. Okay, it's okay. Yeah, extraneous solutions are sort of they're not rooted in math. Okay, anyway, so I have more examples, but let's actually get on to the topic for today. So basically my point was that absolute values can act as a mirror. So basically they can reflect your normal linear equation, right? Your linear graph like this. And the nature of the reflection, where the reflection happens, depends on those transformations that we're talking about. So we're gonna get a lot more practice with this, okay? I don't think there's much graphing on the homework, so this shouldn't be a big deal, but I wanted to get you all exposed, okay? So I had some more examples you can see, but let's move on. And there is a quiz today, so I want to give you time. So the real topic, and the reason I'm moving on is because today's Wednesday and the homework is due Friday. And I want to give you all like enough information to really get through this assignment. Tomorrow we'll sort of cover the loose ends and go a bit further. So dimensional analysis, it's a whole branch of study actually. One of the professors I had in college went to Caltech for his postdoc, and he had a class in physics, and he had a class called dimensional analysis. And then this is a like post-grad class, which is really intense. And basically all they did in this class was they didn't even lift their pens, or they didn't even write anything. Okay, so sorry, I'm getting distracted by the things in the chat. Yes, there is a meeting Thursday. Yeah, this class meets Monday through Thursday. So tomorrow at 10. Sorry for the distraction. Okay. Yeah, so it's a full branch of study. So like what they did in this class supposedly was they just used order of magnitude estimates. So what that means is like they would say, okay, the sun is, this order of magnitude heavy. The Earth has, the Earth is in the order of magnitude of million tons. Okay, so they would use like sort of estimates, and then they would just sort of analyze the dimensions of answers to come out with actual physical results. It's really fascinating. It doesn't involve any calculus or any algebra even, really. I mean, it's a whole branch of study, and ancient people really liked this idea of dimensional analysis because it's rooted in physics, actually. So this is the most physics kind of related things. You might have seen this in your science class. This is actually really like physics, but this is on the SAT. Okay, so math, the field of math doesn't have dimensions, so to speak, like in the sense of meters, seconds, kilograms. Math just has numbers. In math, all of these things are what we call scalars, right? Because these are just numbers. Like you can have 1 meter, most humans are like about 2 meters tall. So 2 to a mathematician is a scalar, but to a physicist, 2 meters is a dimensionful number, right? It has more meaning than it does to a mathematician. Similarly, there are 60 seconds in a minute. To a mathematician, 60 is a scalar. To a physicist, this is a unit of time. It has dimensions. Okay, so on and so forth. So anyway, it's also just an everyday skill that today I'm going to go to the grocery store to buy some food. Like I'm, venturing out to the grocery store as we're doing these days. And I'm going to weigh the vegetables, right? And so if I know that some vegetable, if I say I have the recipe in kilograms, and if I know that I need, 3 kilograms of, that's a lot, of asparagus or something, right? And everything in the grocery store is in pounds, then I need to know how to convert from kilograms to pounds. The way you actually do this is you multiply by 2.2, I think. Okay. I think that's how you do it. Okay, so we're going to figure out why, what makes this process kind of what it is, how this works. Why would I multiply this by 2.2, for example? Okay, so that's the topic of the rest of today. Make sense, this introduction?
Yeah.
Okay, good. Okay, 12 inches is how many feet?
1.
1.
Yes, so I should really write, this is so slow. Yeah, 1 foot. I shouldn't even write feet. It's singular. Okay, good. So this is kind of what we call an identity, okay? Because it's the most basic way to get from one unit to another. So if I were to ask you, how tall are you? You would probably tell me in feet, right? Maybe you're 5'5", right? That's 5 feet, 5 inches. And if I want to know what this is in inches, see, this is a mix of feet and inches. If I want to know what this number is in inches, like if you go to the pediatrician or whatever, they'll always measure your height in inches because it's 1 unit instead of 2. See, feet, inches. If I wanted to know what this is in inches, then I would have to, well, see, look, this is already in inches, but this is not, this is in feet. And if I know that 1 foot is 12 inches, then 5 feet is how many inches? What do I need to do?
65.
What's 12 times 5?
That's just 60.
Yeah. So what I would need to do is I'd have to multiply 5 by 12 because 1 foot, they're 12 inches in 1 foot. And so if I multiply this entire equation by 5, then this side becomes 5 feet, and this side 12 times 5 is 60. So yeah, so this would be 60, and then you're plus 5 inches, from this little bit that I didn't account for, gives you 60. So yeah, so you'd be 65 inches tall. So this is sort of the big picture. This is what's happening, right? So now tell me, how many feet are in 6 inches?
0.5.
Yeah, and so some people, I think this is very simple for some people. But look, if I have this equation that we started with, that 12 inches is 1 foot. what if okay, how do you get from 12 to 6? You divide
Just
by 2.
half
right?
it.
Yeah, so if I divide by 2 on this side, then I have to divide by 2 on this side. And so 1/2 of a foot is your right answer, which is the same thing as 0.5 feet. Make sense?
Yes.
Someone else tell me how many inches are in how many feet are in 3 inches?
1/4.
Very good. And how did you do that? One way to do it, certainly. We're actually going to abandon this method eventually, right? How do you get from 12 to 3? You can divide by 4, right? And because you divide by 4 on this side, you have to be fair in algebra, and you have to divide by 4 on this side. And 12 divided by 4 is 3. And indeed, as you said, this is 1/4 or 0.25, whatever, right? How about this one?
12.
0.08333.
Okay, so those are both, okay, so 12 is not right. That would be a bad,
1/12.
I said 1/12.
you said 1/12. Okay, that's much better, much better. Okay, so the way you would do this using the old method is instead of there being a 4 down here, just replace it with 12 on both sides. And that'll give you the right answer. That 1/12 of a foot is 1 inch. Now here's another approach. Say I have 1 inch, right? It's equivalent to this other approach in blue that I wrote up there. But this is sort of the way that is more efficient, maybe. Same idea though. 1 inch. What do I need to multiply? So I want the final answer to be in the dimensions of feet. Now remember that if I multiply, if I have the number a, and if I divide it by a, say if I multiply by 1 over a, that's the same as dividing it by a. What is a over a?
1.
1. And so if we can I don't want inches in my final answer. So if I can divide by some number of inches and then multiply by some number of feet, then inches cancels and I'm left with the dimension of feet, which is what I want. So if I put 1 inch in the denominator, what needs to go in the numerator? Okay, we need to find some conversion factor, right? And the conversion factor that we started this entire discussion with is that 1 foot is in 12 inches.
I have a question.
Go ahead.
So on the SAT or ACT, is there going to be a math chart, a measurement?
I think they're going to expect you, so they're going to give you basic area, area of a triangle is 1/2 BH, area of a cube is the side cube. They're going to give you, I think, basic stuff, which I don't think when I took the SAT, I didn't even look at that stuff.
I have a question.
Go ahead.
So on the homework,
Okay. You cut out.
It was convert light years to mega light years. Do we need to know that for the SAT and the SAT?
That's a good question. If they give you obscure units the way I did on the homework, they will give you sort of the conversion factors you need. But if I were you, I would just keep in mind that there are 12 inches in a foot and that there are
the basic stuff.
The basics, that there are 60 seconds in a minute and that there are 60 minutes in an hour and there are 24 hours in a day, so on and so forth. Yeah. Alexis says 0.9. I don't know what you're referring to. Okay. Anyway, does the process make sense? So I can what is this number? This is 1, right? Physically, 1 foot divided by 12 inches, that refers to the same, if this were 1 foot, well, that's the same thing as 12 inches. The numerator and the denominator refer to the same length. Therefore, physically, if I divided 1 foot into 12 inches, I get 1. So this number is really 1. So in a sense, I'm preserving, when you multiply something by 1, you're preserving that thing you're multiplying by, right? So generally a times 1 is a. So look, the sort of the essence of this number is not changing when you multiply by some conversion factor. That's the point of the conversion factor. The conversion factor is just a middleman, right? It is 1. Physically, it means 1, but it's 1 expressed in a fancy way, in a convenient way that gets you from inches to feet, right? So the answer is 1/12. Does that make sense? This is the approach that we're going to use, and it's very convenient. So it takes some practice. So let's do that. So 24 hours is how many days?
One day.
1 day. Very good. So that's the kind of thing you should know. Okay, Adi has said, oh, dimensional analysis. Thought we were doing, no, we're not doing derivative properties. That was way beyond the scope of this course. Yeah. Okay. For the seniors who like want to get some calculus, just stick around afterwards. We can talk about calculus. We're not doing that here. Okay. Yeah. Okay, so 12 hours. How would I do this using this new approach? 12 hours, I'm trying to get to days, right? What do I need to multiply to get rid of the hours? Well, I can put hours down here. That'll get rid of the hours. What do I need to put up here then, if this is days?
Days.
Yeah. So
124.
Say that again? 1 over, did you say 1 over 24?
Yeah.
That's right, because they're 20. That's exactly the fact that we were kind of given that we actually know. So this is, in a sense, your conversion factor. This fact is your, did you see that? It just screwed up. I was writing and then this is your conversion factor, right? And I've applied that fact here. See, this is one, this physically is the number 1 because there are 24 hours in a day. This refers to the same amount of time. You have the same amount of time in the numerator as you have in the denominator. Make sense? So what is this? 24 divided by 12 divided by 24 is what? 1 over 2. So this is half a day. Make sense?
Yes.
Okay, I can't like see your faces obviously, so I don't know like how confused people are. Okay, let's do a few more examples. So this is really just the thing you get with practice, okay? So 48 hours. Okay, what is the conversion factor? Someone tell me.
2 days.
Okay, you just gave me the answer, but I want the conversion factor. I want to show why this is true.
Oh, so you put hours in the bottom.
Good, and what's in the top?
Days.
And so what's the conversion factor? It's the same as the last one, right?
Yeah.
What is that? How many hours are there in a day?
2. Well, 24 hours in a day. Sorry. 24 hours in a day, and then 48 hours in 2 days.
Okay, good. Sorry to laugh. The Earth is actually spinning to a stop in a sense. So that a day will be, we don't need to get into that. But yeah, the length of the day is actually like changing very slowly. So in millions of years, you'll come back and a day will be like a year.
Oh, no.
In other words, the Earth will turn once a year. It'll be tidally locked with the sun. So anyway, but yeah, for the purposes of the SAT, this is your conversion factor. Okay. I don't mean to get sidetracked. Yeah. Long, you're right. Yeah. The sun will be dead. Yeah. Okay. So does this make sense? Okay, good. So let's do this one. 36 hours is how many days? Someone else participate.
1 day
one
over.
half.
Yeah, so what's your conversion factor? Days over hours. And what is it?
1 over 24.
Yep, as last time. And what's 36 divided by 24?
1.5.
Very good. Yeah, so I trust that everyone can do this division, but if you don't know how to do it, you can divide both sides by 12. You can divide this by 12 and you can divide this by 12, and then 36 divided by 12 is 3. This is 2. So 3 halves is the same thing as 1.5. So 3 halves days or 1.5 days. Okay, good. Now how about how many days are in 2 hours? So here we're starting with hours and we're trying to get to days. Okay, Alexis, let's talk about this afterwards. I just said like a million. It's actually more than that. Okay, let's talk about it later. I'll tell you. Okay, so 2 hours. How do we get to days? Multiply by what? Okay,
Days
Adi,
over hours.
let's focus here. Yeah, you're right. Days over hours. And what's the conversion factor? As last time and the time before and the time before, what? 1 over 24, right? So what's 2 divided by 24?
12.
1/12.
1/12, not 12. 24 divided by 2 is 12. 2 divided by 24 is 1/12. Very good. 0.08, same thing. Yeah. Okay. Makes sense? So you can see that, intuitively you could probably guess this, but what if I said, what is like 1.46 hours? How many days is it? Intuitively, you would not be able to do this. And this is where this approach makes a lot of sense. You can just divide this thing by 24, and that gives you the amount of time of 1.46 hours in days. Okay. Let's just do a few more. How many hours are there in a minute?
60.
Oh, sorry. I
Sorry.
keep saying this backwards. How many minutes are there in an hour?
60.
So this is your conversion factor. Right? So how would I do this? 5 hours is how many minutes?
So you would put hours on the bottom
Yep.
and then minutes on top.
Yes. And what are the numbers here?
1 minute. Sorry, 1 hour is 60 minutes.
Yep, 1 hour, 60 minutes. So this is the number 1 again, which preserves this quantity, the physics of this quantity, the physical meaning of this quantity. And hours cancels, and you're left with minutes. So the dimensions work out. And 5 times 60 is 300.
3.
So 300 minutes. Yeah? Good. So now you can see, yes, Alexis, you're having a quiz. I'll send it out soon. Just hang tight for, it's not too long. Okay, so similarly, okay, I'll just do this one. 24 hours is how many minutes? Wow.
1,440.
Yeah, so someone figured it out.
Hours on the
It's
bottom.
actually an
minutes on
important
top.
example because you'll need this for the quiz. So basically, so far, all of our conversions have only been one step away, so to speak. Like, 5 hours. I only need one conversion factor to get to minutes, but sometimes you need more than one. So for example, this is not one such example, but let's do this. You can see how
Get the 48 hours into a second. I think that was the.
yeah. No, this is here. Let's.
No, that's still. I mean,
Still
you can
one.
make it. You can make it a 2-step.
Yeah. Let's see. 2 days.
Yeah.
Is how many seconds? So this example will require 2 steps, and I'll walk you through it. So I start with days, and I'm trying to get to seconds, right? So first I know that how many hours there are in a day, right? And then I know how many seconds there are in an hour. So you can see I'll need 2 conversion factors. I don't off the top of my head know how many seconds there are in a day. If I knew, this would be easy because the answer would just be twice that conversion factor. Make sense? So how would I, first I'm going to get rid of the days. And I know that there are 24 hours in one day. So now I'm in hours, but see, now I'm trying to get to seconds. So the days are gone, but now to get rid of the hours and to get into seconds, now I need a second conversion factor, and this is the one we used over and over.
This
60
this one?
seconds. Go ahead.
It's not 60 seconds in 1 hour.
It's
My bad.
3.
You can.
My
This
bad,
is
my bad.
actually a 3-step
This
conversion.
is a 3-step. Yeah, sorry, I'm not with it here.
It's fine.
Yeah. Thanks.
So like 60
Thanks for
seconds
coming.
is 1 minute.
Yep. So I forgot that. Yeah, you need to go to minutes first, right? And then how many?
60 seconds is 1 minute.
That's right. So 60 seconds in 1 minute. So okay. So big picture. Sorry, I might have confused people there. So I got from days to hours, and then I got from hours to minutes, and then I got from minutes to seconds. So 2 times 24 times 60 times 60 is your answer. And someone can do that. And I think someone said it in the very beginning. Okay. So maybe just one more example because I screwed that one up. Here's a conversion. Here's a conversion you should know that 1,000 milliseconds are in 1 second. So if I wanted to know how many milliseconds there are in 24 hours, I would have 24 hours and I'm trying to get to milliseconds. So
4-step.
yeah, so here we go. So hours, what's the next most convenient unit? Probably minute?
Minutes.
So look how I'm doing this. I'm just writing the dimensions first. Okay, now to seconds,
Yeah, and then milliseconds.
and from seconds to milliseconds. So this is actually 3 steps.
Oh yeah.
So yeah,
sorry.
there are 4 terms. It's okay. Yeah. So now let's figure out the conversion factors themselves, like the numbers. So see how we figured out the dimensions? So we know that all these things will cancel and will leave
Yeah.
us with milliseconds. Now let's figure out the numbers. These are all things we know, right? There are 60 minutes in 1 hour, 60 seconds in 1 minute, and 1,000 milliseconds in 1 second. So if you multiply 24 times 60 times 60 times 1,000, that'll
Look
give
at the
you,
answer.
and it's not 8.14. It's a big number. Yeah, it's a big number. Okay, so I'm going to send the quiz. We're sort of running low on time. There are 3 minutes left. Okay, there. I just sent the quiz. The last question is not graded, but I encourage you to do it. It's a challenge. It's a bit more challenging. And if people, I'll stick around here if people want to discuss. I would recommend that you try it because the last question on the homework is basically that question. Okay. Yeah, and Biruk, you just texted me. You just chatted I think the answer.
Can't number 1 be all of the answers?
Okay, I'm not gonna say because it's a quiz.
Well, I mean, it's all 3 of the solutions are there.
Okay, let's see. I'm not even looking at the quiz.
Like, choose the best answer.
Let's see. Let's see. One second. One second. I need to get back to the. Yeah. So on the first question, which
I
of the
didn't scroll down. I didn't scroll down to see that. Never mind. Sorry. I was
Okay,
only looking at the
yeah.
4 answers.
There are a bunch of choices. So just pick the one you think is right. And yeah, and F and G are also options. So if people want to discuss the last question, I can stick around for a bit, but it's not graded. It's because it's sort of like what we'll talk about tomorrow. It's a bit more involved. And then you're free to go. So if you don't want to think about the last question, if you've had enough for today, you can leave.